So, we had a good weekend and got all dried out. So it's Friday morning, it's all the rain, and we start going, driving out, and there's a river across the street that I have to get across to get there. So some of it didn't wash out the whole street, but it washed out kind of a side, but it should be fine. It's all dried out. So. Anyway, hopefully you got the message before coming to the room. So on Friday we were going to talk about, the plan was to talk about some things from chapter 14 and then some things that are mentioned in chapter 24, which we don't specifically plan to have time to go into too much. So the idea of that is that a lot of times there's a design, we have more treatments than you can actually afford to put a lot of replications into each combination, right? So there's one, chapter 14 and 24, kind of this fractional factorial designs are ways of doing ANOVA-like experiments, but when you have more combinations you can possibly fully explore. Sometimes these are incomplete block designs. So a block of subjects or units that you can apply treatments to, maybe there's 4 units per block, but you might have 8 treatments. So you can't put all the treatments in every block, but you can still do things to set up a design. Often these look for balance, so you get kind of the same number of treatments per each, the number of replications per each main treatment factor on each variable, and maybe a balance across interactions. But you don't get enough to estimate every 3-way or 4-way interaction or more complex things. But you still can get a lot of information. So what I would encourage, if you're interested in this, if it's relevant for things that you might be doing, is you could go through the commands there, look for things of how it's describing that for a final project. If this is particularly relevant for you, you could look at some of the things in chapter 24, the data examples there, and go through a little more detail. In one of these examples that involves wear of clothes, there's an abrasion, and there's different treatments, and there's different positions, 1, 2, 3, and 4, and there's different runs, right? 1, 2, 3, and 4, and the positions are a treatment factor, right? And the runs end up being a blocking factor. But then there's treatments also. The second treatment factor is A, B, C, or D, the type of material. And you can't put every treatment at every position within each run. It's just not feasible. So they use something called a Latin square. And in the world of experimental design, there's whole books written on different ways of setting things up. And in this particular problem, in run 1, they put the different treatments in these different positions like this, right? And then in run 2, they put the treatments in the different positions within that run or that block so that you don't get any repetitions, right? So they put A here, B here, D, and C over here. And then within run 3, they put them in a different order, D, C, A, B, and in the 4th one they do B, A, C, D. So in every row, in every column, you get every treatment once. Right? You don't get any duplications, none are left out. So in a way it's balanced. So you should be able to estimate the effect of C versus the other effects. Right? And it's 1 per run, 1 per position, so it's kind of fair for every C, A, and B. Same thing for the positions. The positions have, in every run, have a different treatment. So what's the impact of treatments? You can kind of take the average of those, and it's all balanced that way. But you really can't get much more than that. There can't be many more interactions because there's just not enough repetitions. But you can still do the main effects and control for other things. And so it's kind of a neat theory how it all works out. And so these designs make use of combinatorics and geometry and kind of groups and permutations of things, very much like Sudoku and other things. But anyway, if you're interested, that's what we were going to talk about. And you could go through some of the commands for some examples, and it might be a project if you wanted to, if you wanted to investigate that more. Right? So chapter, part of this class is also, reading the book, looking at some of the examples, getting some of the concepts, and we talk about part of it in here. We don't necessarily work through every example, but the data are available, and assignments have you think about that, some of these things. But we're going to move on to thinking about serially correlated data for this week, essentially. And the idea of serial correlation is correlation over time. So that if y sub t is the outcome measurement at time t, in the problems we've been considering so far have been independent observations. So what you know at time t doesn't tell you anything necessarily about the previous one or the one after that. More often we have an index of I, just a random observation that's independent, but in serial correlation, the correlation between y sub t and y sub t plus 1 is not necessarily 0. So that you can get, if you know that the y sub t's are kind of high values for the range you expect, the next ones are either, if they're positively correlated, or tend to also be in that high range, right? A negative correlation would mean that if it's high, it tends to go low and kind of oscillate more, right? And both things happen. And so if they're not independent, right, then our ordinary things are just taking an average. You can still take an average, that would be a fine thing to compute. But the standard error, because these things are no longer independent, doesn't work out quite the same way. The S over square root of n no longer is necessarily accurate. It can be vastly inaccurate. So comparing averages across two correlated series becomes a challenge, right? And so these types of data sets are sometimes called time series, right? Where you're taking measurements, but there's variability over time, or variability over, it could be a manufacturing process, and things are made one after another. And the quality of at one time period is a pretty good predictor of quality at the next time period. But then something breaks or something drifts, and it kind of goes, follows that. Right? And so we want to take advantage of that correlation, recognize it. There's some special models that we're going to consider. These are called autoregressive models. So autoregressive, so kind of self-regressive, or where a series is predicting itself. Right? The kind of a generalization of this would be spatial models, right? Which has a whole area of statistics that's beyond what we're going to do, but modeling things in the environment, and you have a spatial layout. Right, then the temperature or the pH in one area, or the cyanobacteria in one part of Lake Champlain is probably related to what's nearby, but it's less related to things that are farther away. And modeling all that becomes really quite complex. Things are not independent, but there's theories that develop things like that. Right? So one thing we can consider, right? Let's say that we have y1, y2, right up to yn, and we're interested, our interest is in the average of this series. Interest in mu, the average for the series. And we can consider just taking y bar as the estimate, right? If they are, if the y sub i's are independent, then we would typically have the standard error for y bar is just the sample standard deviation of those things over the square root of n. Right? But if the y sub i's are not independent, the standard error is, under some models, would be estimated as this s over square root of n, but with an adjustment. And the adjustment is related to something called the first order serial correlation, or the correlation at lag 1. And it's 1 plus this R1 over 1 minus R1. And this R1 is called the first serial correlation. First sample serial correlation. Right. Roughly, it's like the correlation between the y at the current time point and the y at the previous time point over the entire series. There's actually n-1 pairs at lag 1. The difference between the time points that you're looking at is called the lag. Pairs. So if you're taking today versus tomorrow as a lag 1, either today versus 2 days in the future or 2 days in the past, it would be a lag 2. And some things have a lag of, in effect, it's kind of a difference of 1. Things that are seasonal or periodic, right? So traffic every Monday is somehow related to traffic every other Monday, and Tuesdays are related to one another. So there's kind of a 7-day lag in some things. There could be also seasonal lags and bigger things. Time series, some of the interesting applications are, the long-term solar cycle, long-term environmental histories, like ice cores going back 120,000 years. There's all these different lags. But we're going to do this first order correlation there. You could kind of take the observations you have and take out the first one, and that would give a vector length -1. And take the vectors that you have and take out the last one, and that also give a length of n-1. And if you kind of align them by shifting them 1, and you can take the correlation of those, that would give you something like this. The formula is actually just a little bit different. That's there. And so the formulation we use to compute that one is going to be a ratio of two things we calculate. We're going to calculate the residuals, so using the Brooks notation. It's the yt minus the average for the series. And the C1 is 1 over n-1 times the sum of these, of the residuals at time t, times the residuals at time t minus 1. So this is like a covariance between the residuals offset by 1. And C0 is 1 over n-1, a sum over all of them of the residuals squared. This is like a variance. Right, we're calculating this. And then the estimate of the serial correlation is the ratio of this covariance over the variance. And this one is between 1 and -1. So if the series tend to be kind of stay high or stay low as it's moving along, and they're kind of similar values over time, it's positive. But if it tends to swing more up and down, and a high one means that it's going to go down, it's going to be negative. If there's no serial correlation, it'd be 0. If there's no covariance between residuals at one time or the other. Right? And so what impact is that going to have on the standard error? Right? So R0 is 0, it still doesn't have anything, right? So it's just the regular SO squared thing. But if it's positively correlated, right, that means there's a lot more variability over time. Right? And this is positive, and that's nearly 0, so that the standard error can increase a lot, right? Up to the point when R1 is very, very high, it's not like we have very many independent observations at all. They're worth a lot less because you get a few high ones and they all are high, they're all low. You might just kind of have practically 2 observations if it's at an extreme. On the other hand, if they're offsetting each other so that when you get high values, then you tend to follow by low values and vice versa, the average is going to stabilize faster, right? Because you're not going to be in the tails at the extremes for very long. You're going to pull back toward the middle because of the correlation, and it'll be more stable, right? And that's kind of the adjustment that gets done there, right? So we're going to look at how that happens for a few. We're going to look at some pictures, think about some of the characteristics of different time series, and look at that. Underlying this, like a lot of our statistics and calculations, is a model, right? So throughout this and all these different things, we've got a model. Are the data normal? Are the means equal or not? Are the variances equal? Is the regression line a reasonable model? What's the error structure? There's a model here. So the model that's relevant for this is called AR1. It's an autoregressive model of order 1. And if y sub t, so this model are the values that are measured at equally spaced points in time. There'd be other models called point processes that are not measured at the equal points in time. Right? Or sometimes you can take something that's almost measured equally in time and kind of associate that, right? So if you have patient appointments, people don't come in exactly at the quarters or the half years. They come plus or minus a month. But you might say that that's close enough to call it equally spaced. The book used, let's see, nu equals the long run average of the series. And then y sub t minus nu is a difference of the measurement at y sub t minus that average, kind of a residual, right, the deviation. And so the model says that the average of this thing, the mu of this thing, right, given the past history, is going to be some alpha times the previous measurement minus its deviation. Right? So this is the average or expected value of that. Right? That deviation relative to the global average, and it's related to this but with some alpha. So alpha is called the autoregression coefficient. And then the R1 is an estimate of that coefficient, that correlation. Right? Importantly, this only depends on the lag of one time period. It doesn't matter what happened 2 days ago or 3 days ago or 4 days ago, or you could have a 100-day history, but the only thing that affects the average is where you were yesterday. Right? There's AR2 models, AR3, AR whatever, that you could say, no, we need to know a longer sequence to do that. And some parts of time series is choosing that order. An important model for economics is the autoregressive 12 models that are used in employment and unemployment. Kind of a monthly series, uses lags up to 12. Right? There are other models that don't just have this autoregressive, but also have a moving average over time. So there's a moving average model. You can combine those. You can get autoregressive moving average models. So there they are. There's MA. There's ARMA. autoregressive moving averages, and then there's another there's another I that can go in there for abbreviation. There's an integrated ones that have something else going on. Right? So there's a whole host of models in the time series literature, particularly in economics or weather, that model these things. Right? But that's an expression of the averages. But we can express it a little bit more as we'd expect to see it in regression or something like that. Right? So that model, we kind of one way of, and so this is done more. In 15.3 does a little bit more with this than you'll do today, right? But the y sub t versus minus its mean can be written like a random variable given y sub t minus 1 minus this global average, plus some error. Right? And the error can be independent, normal, 0, some sigma squared in there. And so the yt could be thought about as being regressed on y sub t minus 1, the previous ones, and get something like that. So in this case, the expected value of this y sub t minus nu, right, is going to be alpha times, given y sub t, if that's a number, kind of the, given that we've had, given the past history, treating everything in the past history as a number that we've seen and recorded and know, right, plus 0, right? So the expected value of our errors dependent on that would be 0. And in the covariance between, the probability theory would say that the covariance between y sub t and y sub t minus 1, well, y sub t minus 1 is related to y, well, this one's related to y sub t minus 1. There's an alpha in there, and then there's going to be a variance of y sub t minus 1. Right? The covariance, this alpha comes in here, and what we do in the R1 estimate is we estimate the covariance by that first term, and we divide by an estimate of that variance here, and that's how it works out. So what I like to do is just look at some examples, look at some plots, look at some examples that kind of bring out some different things that would be happening with time series and some interesting things that hopefully is kind of interesting. And then on Wednesday and Friday we'll look at more at models and estimation and data analysis for things in a little more detail. Estimating this, confidence intervals for that, hypothesis test about that, and a few extensions. Okay. Yes?
Do we still have a homework due Friday or not?
I guess I haven't written that yet. I'll have to think about that. I have an exam in the other class, so I kind of space that out. But it's
I was just wondering because it said on Canvas, but because of
the
class.
next one would come. Yeah, right. I'll double check.
Okay.
Right. So whether
So I was wondering if it got pushed because of no class on Friday.
If we did, well, I don't know. It might make sense to, but I'll look at it and try to tell you something soon. But it would, the plan is to have it mostly on this correlation things, and so. But yeah, I'll try to update you. Thanks for asking about that. So, in looking at some of these, we're going to look at some of the data sets that are in R, and data just gives you that list of a bunch of things, right? And so in R, of course, there's a bunch of data. And some of it, air passengers, has a time to it, some of these other things. Any one of these data sets in there, you can have help with that variable name and get information on it. Right? And so one is the seatbelts, road casualties in Great Britain, 1969 to 1984. Right? And it has, the seatbelts has a bunch of columns, drivers killed, number of drivers, where did they go, kilometers, so a bunch of these. And the plot did a plot of a bunch of variables together, right, to kind of recognize it. And so you get this kind of pattern, it's kind of going up and then down and up and down, and so it does not look kind of independent over time. And this is a little bit smaller. And what was this? I can't really tell what that one. Let's look at the names of seat belts, and that will help. Oops. It's a time series thing. So time series are this like a little bit different structure. Oh, it's by monthly. So let's see. Dim names. It's not going to call it a seat belt. And then the second one of those are the names. So drivers kill, drivers, front, rear impacts. Kilometers driven. Why do you think it has kind of that pattern? Monthly data.
Seasonal.
Huh?
Seasonal impact.
Seasonal impacts. You're traveling for summer maybe, right? And maybe just a general increase over time. Petrol price, so gas price, 1974 or something, oil crisis, showing things up. Van seem to have gone down, deaths gone down. So maybe there's safety factors going into this, and some type of law about seatbelts. Right? Did it make a difference? So you get some of those. You can take the average of some of these things. So 122 is the average deaths per month. There are 192 rows, or 192 months in that time period. You take the standard deviation over the square root there, you get 1.83. So that would be the standard error if we didn't account for serial correlation, if these things were independent over, but they kind of follow and you kind of see a definite pattern. There's a command in R called ACF, useful for time series, that computes autocorrelation function. Right? So it'll calculate the correlation at lag 1, at lag 2, and lag 3, and then see how kind of sticky this is over time. Right? So the plot is here. Right? So the first, that one at 0 is just correlation with itself, which is just 1. Right? Correlation of anything with itself is perfect prediction. But this is the second curve here is R1. Right? So about 0.6 as a correlation. And then at lag 2, there's a correlation. Lag 3, there's a correlation, and so. And then, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. At 12, we get another correlation that's kind of high. Right? So it's kind of this periodic. But if you just look at the first one, it would be kind of an inadequate model given the seasonality. But anyway, you get that one. The second value here you can pull off is 0.625, right? The correlation between the seatbelts, kind of just augmenting them, will almost get that, but it's not quite the same because it would only use n-1 pairs. But the thing we use in the denominator is actually the variance of all of them, so it's just a little bit different. That's why that C1, C0 ratio is close. And I thought, well, I'd like to do that, to calculate that for some different series without having to necessarily use the ACF. And I thought about doing it by hand, C0, C1. And so if I'm going to do this a lot, I'm going to write a function. Yeah.
So I'm confused. What is the negative 192 and negative 1?
Well,
I'm not sure if you specified.
Yeah. So in the data set, right? So the what we have here is 1, 2. This is y sub t, 192, right? And what we want to do is correlate this value with the previous one, right? Well, at 1, there's no previous one, or something like that, right? Right. So if you think about shifting this off to the side, so that this would be number 1, and this would be number 2, down to 192. This is 191, right? So we're comparing this to its neighbor, or comparing this one to its neighbor, or comparing this one to its neighbor. So one way to get that into R, well, if you see we have these two left over that don't match up when we take the difference of one lag. Right? So if we cut this one out, that is -1. If we cut this one out, that's 192, taking that out. And then we do the correlation of the rest to kind of offset it by 1. And the minus means take out that row. So. But that's not exactly what is the standard estimate for R1. Close in a larger data set. But I wanted to do that, so I wrote a little R1 function. If you do something a lot, or want to do it with a certain way and get extra things, like the sumword command in R for a data set doesn't give you the standard deviation. So I don't understand why it wouldn't give you the standard deviation, because you obviously want to know that. So you can write a function. And so the data that's going to go into the function is x. Right? So here's how I would use it, R1.function of my data. And what do I want to compute? I'm going to compute the residual, right? And then I'm going to have the covariance and then the covariance and the variance here, take the ratio, and my output, what's going to come out of that, the last thing that is in that list of things, is what is returned by the function. And you can return a vector of things or a list of things or more things all at once, right? So you can return more. But this is like the -1 minus n, right? Is that numerator there, and then the sum of those things squared, and that's my R1. So when I do that function, right, when I do this, right, when I type all that in and then do run, it creates, so now R1.function is a function that exists there. Right? And I put it in x, and it will apply the function to whatever's there. And so when I do that for this, my driver's killed, I get the 0.625 number, which the autocorrelation function returned. What impact does that have on the variance, the standard error? Well, here's the adjustment factor, 1 plus R1 divided by 1 minus R1 in the square root. It would be double in the standard error because of that correlation, right? And so the correlation, is the standard error now would be more like 3.8 instead of 1.84. That's a pretty big, doubling the standard error could change confidence intervals and significance and have a pretty big impact on things. I wanted to do a little bit more with the function. See, gee, I'd like to get that stuff too when I do this. It'd be nice to be able to get all that. So I modified this R1 function. I calculate R1, I calculated an adjustment. I'm going to calculate the ordinary standard error, right? And then I'm going to take the standard error times the adjustment, right? And I'm going to put it in a data frame. So the thing that I return is that list of different things. And the data frame is nice because I can name the different objects. So I can do a calculation here, but my output won't show me the kind of cumbersome formula. It'll show me everything kind of neat and tidy. So this function, when I do that, and then I do the R1 function applied to that, here's R1, here's the adjustment. Standard error goes up by 2, standard error was this, now the adjusted one is this bigger value. So I don't know, it's kind of like a little thing that I can do to automate a little bit of computation. So anyway, that's one example. You could look at many of those other variables. I think most of them are correlated positively pretty strongly, maybe not petrol price. Well, petrol price kind of has a stickiness, right? So it doesn't change for a while, and then it goes, and then it doesn't change. So that probably has a positive correlation as well. Here's another one, EU stock markets. Right? Closing daily prices of major European stock indices, 91 to 98. Right? The DAX, Switzerland, France, and the UK, the FTSE market up there. So this is 1,860 observations. And this gives plots like this. It plots all the 4 variables, right? So is this going to have high correlation over time? Yeah, that's really high correlation, right? It's almost constant. Like in a little area, it's not changing at all relative to the range, right? More noise, 98, and after that, big increases. The ACF functions, right? Zero correlation is almost 0.99, right? Really, really high, right? R1 function, 0.998. So in comparison to taking what's the average FTSE over this time period, right? The standard error, if you just averaged 1,860 observations together and pretend they're independent, is going to tell you the standard error is 22, 23, right? But if you adjust for the zero correlation, right, it's 33 times as high, because if you're just trying to estimate this overall average of one of these, it's not like you have independent observations that are giving you extra information every time you get an observation. The observation you know, a year later here tells you almost nothing new, right? So it kind of has that impact. We did look at this Longley data at one point. That was, that's very, very small, isn't it? It had GNP deflator, GNP, employment, armed forces, population year, employment, and particularly versus year, a bunch of these variables are highly correlated, right? There is a time series structure there. We did regression without necessarily really considering that. In this particular, like GNP as one particular gross national product, over time, had a correlation of about 0.79. Right? So if you're trying to report average, it almost doesn't make sense in these cases. The average level is not so interesting. As a summary, it's not really well determined because of this autocorrelation. And the bigger thing that's of interest is the change over time and how it's related. If you look at a few other pictures, air passengers, some things have a seasonal pattern. Right? What else seems to be going on with this one?
It's going up with time.
It's going up with time. Any other change?
The spikes are getting much larger.
Yeah. We kind of have this increasing variability over time. The highs are getting higher, the lows are getting lower, right? And that's back in the 1950s, so it's kind of historically interesting. Air miles, right? So this gives a nice smooth curve. One thing you can do for some of these things is like, where are the observations, right? Type equals both, will put in the points, right? So it actually shows you, the data points that make up that smooth line. Because the question would be, is that data, what's the period? And it looks like about maybe one per year in there. There's this other one called sales data. The help file, do not run. For some of these, it's hard to know what they are, but BJ sales, what does that mean? So there's 150 observations. This particular one comes from a book called Box and Jenkins. So Box and Jenkins, George Box, and I'm not sure. But these two books, just in terms of references, are two primary textbooks in terms of time series. The Box and Jenkins models, and this Brockwell and Davis have been, I think, very influential textbooks over time. If you ever studied time series as a research topic in graduate school, whether it's in economics or statistics or related fields, surely those books would be important there. We looked at some air quality data for regression. So these are measurements in New York City of air quality measurements, and one measurement was ozone. Here's just a scatter plot of the data. This object is not saved in R as a time series, so it doesn't necessarily connect it with lines, right? But this index is date, right? Is related to date. So this would be just the plot of ozone, right? See, there's only one variable there. That's taken as y, and then it gives the numbers 1 through the number of rows. Is there a pattern in there? Is there a time series pattern? Solar radiation was a pattern. If you make it type both, you start to see, you can see the up and down a little bit better. If you make it a line, it takes out those extra dots. It makes it look a little prettier, a little easier to see. Right? So for temperature, is there a correlation over time? You adjust the plot a little bit, and you can kind of see it. It turns out that the correlation over time, the temperature is highly correlated. 0.81, that it stays low for a while, then it goes up, then it goes down, and so on. And you get that. Time series is a little different, depending on how long, what's the period. The period is how often they're measured. So New Hampshire temperature, these are New Hampshire temperatures in years. There's a different temperature that's monthly, and monthly then you see the cycle. Right? If it's yearly, you don't necessarily see the same seasonal cycle. Right? So you change that. This was a measurement of approval of presidents over time. Oh, there's a little gap in there, so there's a few missing values in there. And almost all of these things, so the R1 function, R1, that function of presidents, oops, has missing values. Let's see, made up equals true. It's not used. So I'd have to modify my function there to handle missing data, or take out the missing data in any case. I didn't think about that before. Another example is this Old Faithful data. I don't know, I've used this in different classes. So there's eruptions. How long does the eruption of the Old Faithful geyser in Yellowstone go? And then what's the waiting time between, right? And there's a smaller cluster and a bigger cluster, right? And generally after a long eruption, you have to wait a longer time for the pressure down under the earth to build up, enough water to flow into the superheated lava area and create steam and then blow up. So if it's a big eruption, you have to wait longer, and if it's a short eruption, it comes sooner, and people there at Yellowstone can use that to predict when the next one's coming, so you can time to go get hot chocolate or something. But if these things actually are in some type of order, right, because one after another, I don't think that anything in the data set tells you that it is. Right? And so there's only just, waiting times and a bunch of them. Go back a little bit. 272 of them, so head of faithful. Eruptions and waiting time just has those two numbers. It doesn't necessarily tell you exactly what's there. There's a help file for it, right? Waiting time between eruptions. It tells you a little bit there. And there's a few more comments about sources. There's apparently more data on this out there that could be done. Right? But if you plot the eruptions over time, you get that pattern. If you connect them with a line, you get this. Right? So it always seems to go up and down and up and down. Right? So maybe they're not so independent. What happens if we do the ACF function or the R1? Right? The second one there is actually negative, right? Which would make some sense, right? That if, right, the negative 0.55. So after a big one, you tend to get a small one, then a big one, then a small one. That there's some correlation there. That it's not perfect, but it tends to be the pattern. Right? So if you wanted to do the average, you'd actually get better precision, right? Because the tall and the big and the small would kind of cancel out quicker because it's kind of forced that way through the correlation. So I thought it was kind of interesting to see a negative one like that. But it's just amazing how many different different time series things are present in there. And really the analysis of time series is harder than most standard statistical things. So it's kind of interesting that there's that many, to me, that are there. You can do, there's others about levels of lakes, levels of the Nile River over time, generally all positively correlated. The amount of CO2 observed at Mauna Loa Observatory, there's monthly, there's a seasonal variation there. And the number of links that are tracked in, what is links? An interesting data set. Annual Canadian lynx trappings, 1821 to 1934. That's probably the lynx trappings they know about, like get registered or reported, or the sales of something like that, how they would know that in the deep wilderness what's actually happening. It's the 1920s, kind of amazing, so. But anyway, it was included in one of these, a couple of these important things. That plot, like this, shows it going up and down. One thing, and it's very highly correlated over time, 0.71. Do you have any idea what would explain this up and down pattern for the lynx populations? Yeah.
Well, if you trap a lot one year, then there's not going to be as many to track that next year.
Right.
They kind of have to repopulate.
Populate. Yeah, this is all biological problems, kind of a boom and bust. Population gets big, it eats out all the rabbits and everything, and then it collapses, and if it's smaller, then it has room to grow, and that probably relates to the amount of trapping that's going on. And so this kind of a periodic cycle. Right? But how much is this based on? Right? If you plot the points, you can see what these are. That it's not just a low point connected to a high point, or a low point to a high point. There's several years determining the whole curve. So you see a little bit stronger picture. There's some data sets that are in there that will be more like what we will do in later chapters. There's this one on growth of loblolly pine trees. Right? And stored in the data set, right? So they have certain trees, and each tree gets multiple measurements, right? Age 3, 5. These are not separate trees, right? And so that complicates things for analysis, right? Seed number 301, watched it for 25 years, and that's how it grew. They are time series in that sense, but they're also called repeated measures, right? So we will do repeated measures. Interest there is really estimating factors associated with the growth curve. Can you fit a model that says how these things grow? And would that be related to that? This orange trees is a similar one. It's there's 5 trees, and the age of the trees in days maybe, or weeks, and then circumference of those. So those repeated measures, they're like time series, right? But really it's one unit getting measured multiple times as many units. So it'll be a little bit different, but the issue of correlation and modeling still applies there. I wanted to show just a couple more things for today. There are some other sources that you can readily get a little bit more information on these. There's NIST, down in Gaithersburg, Maryland, has an engineering statistics handbook, and in that there's an introduction to time series chapter. So one possibility for a project, if you're really interested in time series, would be to investigate some things that are in here. They talk about moving averages and smoothing techniques. Here's some sample points, Box-Jenkins modeling, and some of these things, there's a series of data, you plot the points, all the correlation function, and go through some kind of analysis to try and estimate things forecasting related to that. And in some of these things, they provide, so there's a data set. Some of these things have R code in them, but they have some formulas. It takes a little bit of looking through that to find out what exactly is there. But there are some other examples that would be there. One book that I have on R is this one by Cowperwade and Metcalf. There's Introduction to Time Series with R. And if somebody's really interested in that, I could loan you the book if you wanted to look at that for a possible project, but or just between them. Could be some other things that we could do in ours. Right? And so it goes through a whole series of commands and things that you might do with time series. And it uses the air passengers data, right? And so this is the air passengers data. And it's saved in R as a time series object. So when you look at it, right, it's monthly and by year, and these are the number of air passengers that are there. There's a number of because it's time series, it knows to plot it versus time and it connects it, makes it look nice. And there's that seasonal air pattern with the increasing things there. The type of object, all the objects have some type of class. It's a time series class. It starts in 1949, month 1. It ends 1960, month 12. Its frequency is measured every 12 in a year. Right? And so that's kind of encoded in the data set right there. You can, that's the plot. There's an aggregate command for time series that is aggregating across rows. Right? So it's kind of adding up the totals. These are the totals by row. If you divide that by 12, you get an average per year. Right? So you can kind of collapse the 12 into one total and divide by 12. And so we get an average number of air passengers per year. And so once you can put those points onto this graph, like this, and there's the points. Right? So there's the average by year. And so that kind of gives you this trend. So besides estimating correlation with time series, sometimes you estimate the change that's going on, right? In this one, there's something to describing the period and how the seasonal pattern in a little more detail, right? Cycle, there's some repetitions of the month, so it just kind of tells you something about the structure that's there. If you do a box plot of the annual passengers by cycle, maybe that would show you something a little bit as well. So these are the months, 1, 2, 3, up to 12. And right, it's kind of losing some of the other yearly pattern. But it's maybe interesting that, here in the summer, the 6, 7, 8, that there's kind of higher variability that's there. That's because the peaks are getting higher in the middle. Less change, right? So the bottom part is moving out there. So there's just other ways of looking at it, right, that you might be interested in doing. What we return to on Wednesday, instead of just doing a regression, right, of this on year, we're going to do things with kind of taking differences and regressing on differences versus change in time, right? And then that, like we're doing with the residuals for estimating that R1, we'll do more things like that to see how things, to get at some of these things. And the final thing is, if you have a data set and it really has a time structure and you want it to make a nice plot for time series and use some of these things, it's just a little work to turn it into a time series object and encode that information into R. So what's kind of interesting, to realize is that every object in R, whether it's a matrix or data frame, has characteristics, right? And that R then picks up on those things and does special things with it, right? So it has number of rows, number of columns for matrices and data frames. Data frames have names of their variables. There's dimension names, possibly for the matrices. And time series has this extra structure about cycle and so on. So this is a data set that has, a monthly data set is unemployment rates in Maine, 1996 to 2006. So a little bit higher for a while, but then dropping back down. I'm going to attach that. Right now, that's just a data frame. It's not arranged as any particular time series. Right? The names that are on that are, there's just unemployment. This layout is a little graphical. That doesn't work in this. Let's not do that. Doesn't work on this screen. We just plot the unemployment. It just doesn't index plot. It doesn't have time here. Right? But it looks like there's kind of this pattern going down here. Is there more correlation over time? It's a little bit hard to see. But if you plot that with a line connecting things, right, then you see this unemployment, seasonal unemployment in Maine. Right? Probably very like Vermont. The difference between winter and summer, the things that are going on. The road crews can work in the summertime, but not the wintertime. The ski industry, the winter sports tourism industry operates in the wintertime, and it affects a lot of people. You can change it to a time series object by putting the data vector you want, telling it when to start, 1996, month 1, and the frequency. If you didn't have months, I don't think you would need this. You can just tell it, if it's just yearly measurements, you can tell it 1996, and frequency equals 1, and then 1 measurement every year. But this thing, right, will give you a time series. So let's see what it looks like now. times month. Time series. So it's kind of put it in pattern, right? Like that other one, just kind of, it doesn't go the entire year at the end, but that's okay. I think it assumes that there's no missing data, like no gaps. I think you'd have to have an NA stuck in there. Like you'd have to have a row that has a missing value if you didn't have that for it to keep it sorted. If you aggregate it, you get kind of the average per month across the years. Right? This is the sort of plot of the main time series. Looks like that, but now it's put in the years that are appropriate, which is nice. If you do the annual one, right, that's the annual one. Right? So unemployment went down and then started to go up again. And this is even before the recession in 2008, so probably another swing up coming up there. You can pick certain times, like you can pick February. There's a way to just take the Februaries or just the Augusts. You can look at a ratio there. That doesn't necessarily tell you too much, but if you wanted to look at are things higher in February versus August, these are the February values, these are the August values. It kind of looks like just August is going to be lower, higher employment in the summer. You could calculate ratios versus the overall average. So unemployment is 20% higher than average in February and 80% less in August. You might divide these up into different things. Versus the U.S., you can make the U.S. a time series through that same period of time and aggregate that and do a comparison. Here's the monthly for Maine. Does Maine track the rest of the U.S. or not? Well, we can just look at a plot. Does that look like it? That's the U.S. Right? So whatever was affecting the U.S., well, there's kind of a decrease here, kind of a decrease here. But, and these are 3 to 6, the U.S. the variability of the U.S. is less. Right? But it's kind of the same pattern, but not quite as much. Right? If you plot the annual ones, I can plot them both, kind of scoot back. This was Maine's annual pattern, right, versus the U.S. annual pattern. So, comparing two time series, you could look at, is there a difference between these? Does one kind of lead the other? Right? If the economy of the United States improves, does then Maine follow, or does Maine kind of go ahead? Maybe California goes ahead of the rest of the U.S. or something, right? So the big states might kind of predict where things are going because there could be a ripple effect from, California is as big as many small countries. So if its economy improves, maybe then neighboring areas will improve. So there could be, which one comes first? They're not necessarily causal, but maybe the prediction sense is kind of interesting. But anyway, so that's a bunch of examples. We're going to be estimating kind of average levels, correlation over time, and then other patterns. And we're going to put this into the regression framework. Plenty of good examples. I think you need, come on up here, I'll get you your stuff. I used the handout. This was yesterday, Friday. And if anybody else has homework, that wasn't, I got a couple of them in my box, but others were handed today. See you on Wednesday.
Thank you.
Yep. Sample, some variables are store specific to department and size, others are broader, that they're, they're like the entire economy, like CPI. So, yeah, so sometimes with, one thing that could be happening with the logs, right, if it's 0, log of 0 is negative infinity, and it would become a missing value. So if they really are just zeros, adding $1 there, will still give you a log of very, of 0, but would avoid so many of those missing values if there's no sales or no department. It would no longer go away. It would be a small value. So sometimes there's tricks, like instead of just taking logs, taking logs of x plus 1, that could make some values not missing, and that would make there would be less missing values. So, yeah, and so even with a large data set, some small differences really can become significant, as you're seeing there. So really a lot of variables end up being predictors, and it can be kind of complex, big models because of the big data set. So. Right. The error terms was met. So there are a few extreme outliers, right?
Yeah.
Norm, by the normality assumption. I think that there were a few stores that were really big, had really large sales, and so there are a few extreme outliers. You might want to, most points I think were kind of corresponding, right? So some of them are far away, right? So I think being clear that most of the central part of the curve could be roughly normal, but there's a tail that's extreme, and that could cause a little bit of concern. Yeah, like these, right? So most of it is pretty good, and then there's a tail sticking out there. Yeah.
Far away from.
Yeah. So once you put in the entire group of x variables, their influence, right, could be based not on one x variable, but by a combination of them. So maybe their size was very large, maybe some other aspects of maybe unemployment in that area was very different than others than you would expect. So the numbers, those must be the particular stores and departments that must be correspond to the rows in the matrix. So those, yeah, a few of those cases stick out. A couple are labeled up here. So if you looked at those, it'd be interesting to see, are those, well, probably the biggest stores or extreme in other values.
How are you?
Yeah. Good.